Hello, class. Just wanted to check and see if my microphone was working. I have my cup of tea. First lecture of the morning. Although I have to admit, they still have me go into meetings and stuff, so it's a little bit later in the morning than it would have been otherwise. However, two great lectures in a row I have put together for you. And you probably think, well, he's just doing it like he would teach in class. No, that's not true. These lectures that I put up on YouTube actually take about 3 hours, 2 hours, 3 hours. I put the things together beforehand so that I have a really prepared lecture that's going to go into an archive of video lectures on YouTube that really, will be not only for you, but will be for the public in general. And, after teaching for, um, 30, 40, 50, 60 years like I have, uh, it's nice at the end of my career to finally do this and put it out there, for the public. And Wentworth, of course, in their infinite charity, giving us the intellectual property rights of what we in the Federation, that's our union, feel is our intellectual property rights anyway. So, two great lectures. One lecture on Y delta conversions, and of course delta Y conversions too. And why are these so important? Let's just draw the two things that we're talking about. So when we sometimes find ourselves in a situation where it's neither just series and parallel, and we have to come up with an equivalent circuit that will then allow us to solve the problem that we're looking at in the circuit. The bridge, as it was pointed out in your book, in chapter 2, in the end of chapter 2. And really, I want to start taking on, a lot of times in your book, they'll have topics that during the regular network theory course, I probably, wouldn't go into their more of the topics. I'm going to label these two. 1, 2, 3, right? That's the resistor number. And that's your T or your Y connection. Okay. And I also want to connect these, and this is similar to what was done in your book. This would be like my input, one connection. I'm going to run another connection, just a bus line down here that would be connected to ground or connected to whatever voltage it would be down there. I'm not going to actually put ground because then it might think that you might think that it only works with a positive voltage above ground or something like that. And of course it doesn't. It works with any configuration that you have. And there's a great topical area, and I'll say this too about the book. Not a lot of now this would be 1, this would be 2, 3, 4 over here for this schematic. There let's just put a line between those two schematics. And then I also want to label these resistors too. That would be resistor A, resistor B, and resistor C. All right, so two different ways to hitch up two different parts of a circuit, right? This would be 1 and 2, that would be 1 and 2. So sometimes we have to replace configuration, a resistor configuration like this, with a configuration like this, so that it'll be easier to solve for, voltage drops, current flow into certain parts of the circuit, and we'll look at that later on. This will probably be about a 2 lecture because this is so important. I want to, I'm gonna put the top on my pen to show you how important this is. Now, remember a long time ago when you were a young kid and you finally found out about negative numbers, right? Now you probably thought, oh my God, negative numbers? I'll tell you a short anecdotal story about that. When I was a young little kid, I think I was in first grade, I was with my family driving up to the Upper Peninsula of Michigan to see my grandparents. And I was showing my sister in the back of the station wagon, and no, we didn't have any child restraints during those days. We were lucky we had a station wagon. That I knew how to add and subtract. And so I showed her, okay, 1 plus 2 gives me 3, and I showed her. And so she says, as she was getting bored by my constant questioning of her, she said, okay, what's 2 minus 3? And I thought, well, that's not possible. It's not possible at all. And of course, she told me it was -1. And then that started a whole new understanding of the world for me. And I didn't realize even at that time what that tidbit of knowledge would do to expand the horizons of what I understood as reality and my capabilities to handle that reality. And this is the same way. Right now, you're saying to yourself, why do I have to know this type of change of the circuit? Why is this, and understanding Y to delta conversions and delta to Y conversions, so important for my electrical engineering career? And the reason for that is 3, I hope I spelled that right, phase power. That's right. When you're thinking of electrical engineering, I think a lot of you are thinking of um, computer engineering, microprocessor engineering, fiber optics engineering, right? But there's a whole power industry out there, and the power industry is going to need you to know how to do this transformation between that. And you'll get a lot more of that when you get into motors and controls and your power courses that you're going to have. All right, now I've drawn it this way. I'm going to draw another thing. I'm going to do this. This is like I'm giving you the punchline to the, I forgot to put the timer on. We can rectify that. Yeah, let's say, okay, go. So, what I want to do is I'm going to give you, like I said, the punchline to the whole lecture beforehand, because this is something that people in power engineering, I want to draw this correctly. Giving myself plenty of room there. There we go. Now you're probably saying, "Hey, my God, that's just the delta that you drew up there already." Yes, in some ways it is. It is the delta that I drew up there already. Let me just put. I should have put that out a little further. Oh, I've got my thing that I fixed. So let's just use it there and stick the number 1 out here and 2, just like we did before, 3, 4. So really I've redrawn this whole thing, haven't I? Now, what I want to do is I'm going to create another node here. This is really just more or less a schematic that shows, I'm just going to label these the same that I did on the thing up top. And this also follows along with your book. It's a pretty standard convention of, numbering and working with delta to Y and Y to delta conversions. And that's the reason I put that there is because this is sort of, God, what is the word? The mnemonic? I don't know. It's a figure that helps us. Just like if have ever had vectors in Beer and Johnston, they came up with this I hat, J hat, K hat, which allows you to then cross multiply the independent unit vectors. If you go around the correct way, they're positive. If you go around the clockwise direction, of course, the cross products are negative. And so it's just one of those, right? But that doesn't look like a very good 2. That's a 2. Anyway, I'll be referring to it because these are resistors. I should really put R sub 1. Let's do that. R sub 1, R sub 2, R sub 3. I'm not going to write that all of the time. R sub C, R sub B, and then R sub A or whatever over there. So the T or Y configuration of the connections between these connectors and the delta configuration. And then the figure that helps us remember all of the equations between the two. But first of all, what I want to do is I want to derive the equations, at least the equation, and show you the method to derive the equation for, the first one. Now, if I'm looking at the route, right, let's look at the summation of the resistance, right, and in the route from 1 to 2. So I'm going from here down to here. What are the resistors that would be in that route for the current to go down, right, through there? So from 1 to 2, I would go like this, wouldn't I? I would go through R1, through R3, and then I would be down here at 2. And as a matter of fact, since 2 and 4 are connected, summing the resistors between 1 and 2 is the same as summing the resistances between 1 and 4, isn't it? So we don't have to do that again. Those are not independent equations because 2 and 4 are short-circuited down on the bottom of this figure, as everybody can see. So if I was to sum the resistances for the T connection along that route, I would have R1 plus R3. All right? Does everybody see that? Now, what would I have to do if I was looking at the connection over here? Now, there's 2 different pathways from 1 to 2, isn't there? There's this pathway here, that's R sub B, but then there's another pathway that goes through the series of R sub A and R sub C on the pathway down to 2 or 4. So when we look at the other pathway that's down there from 1 to 2 on the delta, we know that we've got 2. We've got R sub B and we've got R sub C and R sub A. Now, before we even go any further, I just want to look at a rule that I've been applying with current divider and voltage divider analysis in the earlier lectures. But let's just look at what, and I'm gonna look at it for 2 resistors. It could simplify two resistances in parallel. So let's say that I had 1 resistor. I'm not going to call it any of those resistors. I'll call it R sub Z. And I have, and whatever value it is, we're just going to put a symbolic variable in there. And then I've got R sub Y, right? 2 resistors I'm not going to use any other place in this lecture. I've also noticed that pen is getting a little bit not so good, so I'm going to see if I can try another pen. All right, so we've got two resistors in parallel. How would I find those? Well, that would be 1 over R sub z plus 1 over R sub y, right? 1 over R sub z, and that would equal 1 over R equivalent, right? Well, you know, I can't really add these two together because they don't have common denominators, do they? But I can give them common denominators because I can say that this 1 over R sub z is really R sub y over R sub z times R sub y, right? Plus, and I can do the same thing for this. This is just R sub z over R sub z, R sub y, right? So I think everybody can see that this is R sub y plus R sub z over R sub z times R sub y, right? Yeah, this pen's no good either. I'm going to pop that one over there. I've got more pens, but I think they're all, they have to go into the acetone bath. That's what I do. I take the tips of them, put them in an acetone bath, and then just let them, turn them upside down and soaks in. Then they're all great again for, more lectures. However, let's get back to this. So you can see that. But what does that equal? That equals 1 over Req, right? So then if we have two resistors in parallel, the rule is that the equivalent resistance of those two, because we want to take the reciprocal of this, is R sub z, R sub y over R sub z plus R sub y. I think the first pen was the best. Anyway, I'm back to the pen I used a long time ago. Maybe it has gotten better in the meantime. So that's what we've got now, right? R sub z times R sub y. And we've got two things here because in this case, R sub y is R sub c plus R sub a. So that's what I'm going to do. So when we look at the y or the delta configuration, we see what is R sub z? That would be R sub b. And then what would be R sub y? R sub y would be R sub c plus R sub a. Right? And then what's in the denominator? Well, that would be those two added together plus this one. Well, isn't addition commutative? So R sub c plus R sub a plus R sub b, well, we can just write that all out. So R sub c plus R sub a plus R sub b, or all of the resistors that you've got there. All right, does everybody see? Actually, that pen's working better than any of the other ones. Does everyone see how that works now? So I've got R1 plus R3 equals R sub B times R sub C plus R sub A, the quantity, divided by the sum of all three of the deltas. So we now have one equation that equates these two different things. Now, let's look at the sum of the resistances, but now let's look at 1 to 3. Right? I'm going to use a different color pen. I'll use the green pen. So now what we're really doing is we're looking at this circuit here, 1 to 3, right? And if you look at it on the delta, 1 to 3 goes that way, but doesn't it also go this way? Those two in parallel? So now it's R sub C times R sub B plus R sub A. Does everyone see how that's going to change? So let's do the first one first. So if we're just going straight through on the T connection here, it's going to be R1 plus R2. So R1 plus R2. And then if we look at it over here, we've got the same thing, R sub C and then R sub B plus R sub A. So this is going to be instead r sub c instead of r sub b, like it was above. And then it's going to be r sub b plus r sub a is the two. And on the bottom, I've still got r sub a plus r sub b plus r sub c, just like we had in the other one. And now we want to do 1/3 way, and that's going to be to sum. I can never draw those with that top. Why can't I draw? Yeah, there you go. We want to sum R3 to 4. And if you look, and I do have another colored pen here, a blue pen, we now want to go from 3 down to 4, right? 3 to 4. So if we're going 3 to 4, I've got one direction there, R sub A, and then I've got another one. Boy, I should have put these further apart, shouldn't I? I've got another one. This is the blue that's coming down there. So this one and that one, two different ways. Now I've got R sub A times R sub B plus R sub C. If you can see how the trend is going with these. So this one is just going to be R2 and R3. So I've got R2 plus R3 is going to equal, and this time it's R sub A, right, out in front, times R sub B plus R sub C. And again, the whole thing divided by R sub A plus R sub B plus R sub C, right? So I think everybody can see where this is going, because now what I want to do is I want to look at these, I haven't really used red to outline important equations before, but I just thought, yeah, this is probably the best way to really give you, an idea of how we're going to put these three equations together. This being equation 1, this being equation 2, and this being equation 3. 3 different equations that we have. Now, I want to subtract this equation from this equation. Let's do that. Let's subtract this equation from this equation. In fact, isn't it great that I put this equation under this equation so that we can just subtract it, here and really see what we're going to do. So if we take the sum of 1 to 2 minus the sum from 3 to 4. Let's look on the left side of the equation first. So I've got R1 plus R3 minus R2 minus R3. Well, isn't R1 plus R3 minus R3 going to wipe out R3? So isn't it really just R1 minus R2? I know I've taken you through quite an algebraic thing there, but do it in your head. I think everybody can see it. I don't have to, go too far. That's just addition. All right. I hope that I'm still recording. Yes, I am. Yep, everything seems to be going well. We'll see when it's over, maybe. Anyway, back to this. So everybody can see that. Now, on the other side, I think everybody can also see that since we're subtracting these two, and they've got the same denominator, that's great, isn't it? R sub A plus R sub B plus R sub C. So it's got the same thing. We're just subtracting the two. And what do we really have up on top now? And I'm going to write these out. I know, it's going to take a little longer. A lot of you are saying, no, I'm already past that. No, I'm going to write it out for everybody. So I've got R sub B times R sub C plus R sub B times R sub A. That's this right here, right? Minus, let's extend that out, minus And let's put this now. R sub A times R sub B plus R sub A times R sub C, right? Now these are minuses, remember, so that minus is going to extend all the way through here. So I've got R sub A and R sub B is a minus. R sub B, R sub A, of course, it's the exact same thing. So those two are canceled out, aren't they? Does everyone see that? And then what I have is I have, oh, wait a second. R sub, did I do the wrong? R sub A, R sub B, R sub, yeah. Yeah, well, whatever. Just a second. Actually, I was just away for a second. I just had to do a mind grasp here to make sure that everything was working out fine. I'm going to write it down here. So I've got R sub C times R sub B minus R sub A. And where did I get that? Because I had a R sub B, R sub C, R sub A, R sub C. I took the R sub C out of that, which left me with R sub B minus R sub A, just so everybody knows where I am. And then that, of course, is over R sub A plus R sub B plus R sub C. And that equals R1 minus R2. So let me put a blue, I hope that's coming out as blue. Let me put a blue box around that one. Okay. Now I'm going to add that one to this one. We're going to add these two together. I think you can see what we're doing here because adding these two together is going to take R1 plus R2 plus R1. So that'll be 2R1 minus R2, which is going to cancel out the R2. So if I add those together, I'm just going to put add to R1 to 3. Oh, forgot my summation mark, which I can't make very well anyway. And let's put a little arrow there as to what we're doing. So that's where we're going, and then we're going over here to finish that off. All right. So actually, we'll leave it there. So let's finish that off. I want to add those two together, and I think you can see on the one side, I'm just going to have R1 left, right? R1 plus R2 plus R1, that gives me 2. Oh, excuse me, 2. I'm going to have 2 R1 left, and I'm going to get rid of R2. All right, that's one thing. Now, let's do the rest of this. So let's expand these out because we're adding these together. So I've got R sub C, R sub B, that's the top one, plus R sub A, R sub C. All right. Oh, R sub A, that's supposed to be an R sub C. All right. So anyway, we've got those. Plus, I didn't leave myself a lot of room here, did I? R sub C, R sub B. Well, we've seen that before. Minus R sub C, R sub A, right? And all of that, since we're just adding and subtracting, is going to be over the common denominator of R sub A plus R sub B plus R sub C. I think people can see, and that's why I expanded it out here, because I wanted, I didn't want there to be any confusion as I was going through the derivation as to what's dropping out now and everything else. Right, so I've got R sub A, R sub C, R sub A, R sub C, pow, pow. And I've got R sub C, R sub B, R sub C, R sub B added together, don't I? So doesn't that give me 2 R sub C, oh, I better put some type of 2 R sub C, R sub B on top, and R sub A plus R sub B plus R sub C on bottom. And I think everybody can see what I'm going to do next, because I've got a 2 over here and I've got a 2 over here. So that's going to basically end that. And that tells me that R1 in this, R1 in my T connector is going to be equal to R sub C, R sub B divided by R sub A plus R sub B plus R sub C. I hope I got all that. Yeah, I did. Yeah, that looks like it came up there. All right, so that's what R1 is going to be, and I'm going to put a box around here. I didn't really need that equal sign because it's not equaling. I've already got the equal sign there. So that's R1. Now, that brings us back to the schematic that I have over here, okay? Because if you look at this schematic, it's got a delta, and then overlaid on it, it's got a Y, doesn't it? Look at this. R1 equals R sub C times R sub B. How does that fit on our schematic here, right? R1, let's just see what we're doing. R1, we want to find out this resistor, right? So what do we use to find it out? R1 equals R sub C times R sub B. You see the trend I'm drawing here, right? Divided by the sum of all of those. So what we have to keep in mind is the sum goes on bottom all the time. We always think R sub A, R sub B, R sub C on the bottom. But this figure shows us that if we want to find out R1, in the numerator, that's going to equal R1 equals R sub C times R sub B divided by the sum of all of the delta resistors. Okay? How about over here? Let's say we wanted to find R3. R3 would be equal to R sub A times R sub B divided by the sum of all the resistors. What if we wanted to find R2? R2 would be equal to R sub C times R sub A divided by the sum of all of the resistors. Does everyone see the way this is working? And in the next lecture, we're going to look at it, and we're going to see how I can now turn these around and figure out R sub A, R sub B, R sub C. I think everybody can see how we use, how I derived R1. You can go through the exact same process to derive R2, R3, and get all of those now that you know R1 is this. You can always just substitute this back in for R1, and of course then you'd find R2 is going to be like I said, and R3 is going to be like I said too. So I'm not going to do the derivation. I'm only going to do this derivation once, but everybody can use this to figure out what R2 and R3 are in terms of the delta resistors. Okay, does everyone see how that works? Yeah, great, a great thing. I'm going to have another lecture, because this was the Y delta. I should say actually I've got R1 is in terms of this, so this should really be the delta Y conversion, because I'm going to come up with R sub A, and that would be, I guess, the Y delta. So I may have these backwards. All right, but that, in fact, actually I could have done the derivation for the other one on here. It's going to be very, similar, and follow through these derivations too, because this lets you see how I'm working to bring parallel and series resistors together and finding out what the equivalent resistance is and everything else. Okay. Next lecture is going to be the transforming the y into the delta rather than the delta into the y, which is what this one was. See you there.